Nonlinear optics is the branch of optics that describes the behavior of light in nonlinear media, that is, media in which the dielectric polarization P responds nonlinearly to the electric field E of the light. This nonlinearity is typically only observed at very high light intensities such as those provided by lasers. Above the Schwinger limit, the vacuum itself is expected to become nonlinear. In nonlinear optics, the superposition principle no longer holds. Nonlinear optics remained unexplored until the discovery of second harmonic generation shortly after demonstration of the first laser. Nonlinear optical processes. Nonlinear optics gives rise to a host of optical phenomena, frequency mixing processes, second harmonic generation, or frequency doubling, generation of light with a doubled frequency. Two photons are destroyed creating a single photon at 2 times the frequency. Third harmonic generation, generation of light with a tripled frequency. 3 photons are destroyed creating a single photon at 3 times the frequency. High harmonic generation, generation of light with frequencies much greater than the original. Sum frequency generation, generation of light with a frequency that is the sum of 2 other frequencies. Difference frequency generation, generation of light with a frequency that is the difference between 2 other frequencies. Optical parametric amplification, amplification of a signal input in the presence of a higher frequency pump wave, at the same time generating an idler wave. Optical parametric oscillation, generation of a signal and idler wave using a parametric amplifier in a resonator. Optical parametric generation, like parametric oscillation but without a resonator, using a very high gain instead. Spontaneous parametric down conversion, the amplification of the vacuum fluctuations in the low gain regime. Optical rectification, generation of quasi-static electric fields. Nonlinear light-matter interaction with free electrons and plasmas. Other nonlinear processes. Optical Kerr effect, intensity-dependent refractive index, self-focusing, an effect due to the optical Kerr effect caused by the spatial variation in the intensity creating a spatial variation in the refractive index. Kerr lens modi-locking, the use of self-focusing as a mechanism to mode-lock laser. Self-phase modulation, an effect due to the optical Kerr effect caused by the temporal variation in the intensity creating a temporal variation in the refractive index. Optical solitons, an equilibrium solution for either an optical pulse or spatial mode that does not change during propagation due to a balance between dispersion and the Kerr effect. Cross-phase modulation, 4-wave mixing, can also arise from other nonlinearities. Cross-polarized wave generation, an effect in which a wave with polarization vector perpendicular to the input one is generated. Modulational instability, Raman amplification. Optical phase conjugation, stimulated Brillouin scattering, interaction of photons with acoustic phonons, multi-photon absorption, simultaneous absorption of 2 or more photons, transferring the energy to a single electron, multiple photoionization, near-simultaneous removal of many bound electrons by one photon, chaos in optical systems, related processes. In these processes, the medium has a linear response to the light, but the properties of the medium are affected by other causes. Pockels effect, the refractive index is affected by a static electric field. Used in electro-optic modulators. Acousto-optics, the refractive index is affected by acoustic waves. Used in acousto-optic modulators. Raman scattering, interaction of photons with optical phonons. Parametric processes, nonlinear effects fall into 2 qualitatively different categories. Parametric and non-parametric effects. A parametric non-linearity is an interaction in which the quantum state of the nonlinear material is not changed by the interaction with the optical field. As a consequence of this, the process is instantaneous. Energy and momentum conserving in the optical field, making phase matching important. And polarization dependent. Theory. Parametric and lossy instantaneous nonlinear optical phenomena, in which the optical fields are not too large, can be described by a Taylor series expansion of the dielectric polarization density P, T, at time t in terms of the electrical field E, T. Here, the coefficients I, N, are the nth-order susceptibilities of the medium, and the presence of such a term is generally referred to as an nth-order nonlinearity. In general, N is an n+1 order tensor representing both the polarization-dependent nature of the parametric interaction as well as the symmetries of the nonlinear material. Wave equation in a nonlinear material. Central to the study of electromagnetic waves is the wave equation. Starting with Maxwell's equations in an isotropic space containing no free charge, it can be shown that where P(N)L is the nonlinear part of the polarization density and N is the refractive index which comes from the linear term in P, note one can normally use the vector identity and Gauss's law to obtain the more familiar wave equation. For nonlinear medium, Gauss's law does not imply that the identity is true in general, even for an isotropic medium. However, even when this term is not identically zero, it is often negligibly small and thus in practice is usually ignored, giving us the standard nonlinear wave equation. Nonlinearities as a wave mixing process. The nonlinear wave equation is an inhomogeneous differential equation. The general solution comes from the study of ordinary differential equations and can be solved by the use of a Green's function. Physically, one gets the normal electromagnetic wave solutions to the homogeneous part of the wave equation, and the inhomogeneous term acts as a driver source of the electromagnetic waves. One of the consequences of this is a nonlinear interaction that will result in energy being mixed or coupled between different frequencies, which is often called a wave mixing. In general, an nth order will lead to n+1 th wave mixing. As an example, if we consider only a second-order nonlinearity, then the polarization, P, takes the form. If we assume that E, T, is made up of two components at frequencies I_1 and I_2, we can write E, T, as where CC stands for complex conjugate. Plugging this into the expression for P gives, which is frequency components are 2 I_1, 2 I_2, I_1 plus I_2, I_1 I_2, and 0. These three wave mixing processes correspond to the nonlinear effects known as second harmonic generation, sum frequency generation, difference frequency generation and optical rectification respectively. Note: parametric generation and amplification is a variation of difference frequency generation, where the lower frequency of one of the two generating fields is much weaker or completely absent. In the latter case, the fundamental quantum mechanical uncertainty in the electric field initiates the process. Phase matching. The above ignores the position dependence of the electrical fields. In a typical situation, the electrical fields are traveling waves described by at position, with the wave vector, where is the velocity of light in vacuum and is the index of refraction of the medium at angular frequency. Thus, the second-order polarization at angular frequency is at each position within the nonlinear medium, the oscillating second-order polarization radiates at angular frequency and a corresponding wave vector. Constructive interference, and therefore a high-intensity field, will occur only if the above equation is known as the phase-matching condition. Typically, three-wave mixing is done in a birefringent crystalline material, where the polarizations of the fields and the orientation of the crystal are chosen such that the phase-matching condition is fulfilled. This phase-matching technique is called angle tuning. Typically, a crystal has three axes, one or two of which have a different refractive index than the other one. Uniaxial crystals, for example, have a single preferred axis, called the extraordinary axis, while the other two are ordinary axes. There are several schemes of choosing the polarizations for this crystal type. If the signal and idler have the same polarization, it is called type I phase matching, and if their polarizations are perpendicular, it is called type II phase matching. However, other conventions exist that specify further which frequency has what polarization relative to the crystal axis. These types are listed below, with the convention that the signal wavelength is shorter than the idler wavelength. Most common nonlinear crystals are negative uniaxial, which means that the E-axis has a smaller refractive index than the O-axis. In those crystals, Type I and two-phase matching are usually the most suitable schemes. In positive uniaxial crystals, types 7 and 8 are more suitable. Types 2 and 3 are essentially equivalent, except that the names of signal and idler are swapped when the signal has a longer wavelength than the idler. For this reason, they are sometimes called IIA and IIB. The type numbers VAR-8 are less common than I and 2 and variants. One undesirable effect of angle tuning is that the optical frequencies involved do not propagate collinearly with each other. This is due to the fact that the extraordinary wave propagating through a birefringent crystal possesses a pointing vector that is not parallel with the propagation vector. This would lead to beam walk-off, which limits the nonlinear optical conversion efficiency. Two other methods of phase matching avoids beam walk-off by forcing all frequencies to propagate at a 90-degree angle with respect to the optical axis of the crystal. These methods are called temperature tuning and quasi-phase matching. Temperature tuning is where the pump frequency polarization is orthogonal to the signal and idler frequency polarization. The birefringence in some crystals, in particular lithium niobate, is highly temperature dependent. The crystal is controlled at a certain temperature to achieve phase matching conditions. The other method is quasi-phase matching. In this method, the frequencies involved are not constantly locked in phase with each other. Instead, the crystal axis is flipped at a regular interval I, typically 15 micrometers in length. Hence, these crystals are called periodically poled. This results in the polarization response of a crystal to be shifted back in phase with the pump beam by reversing the nonlinear susceptibility. This allows net positive energy flow from the pump into the signal and idler frequencies. In this case, the crystal itself provides the additional wave vector k equals 2I per I to satisfy the phase matching condition. Quasi-phase matching can be expanded to chirp gratings to get more bandwidth and to shape an SHG pulse like it is done in a dazzler. SHG of a pump and self-phase modulation of the signal and an optical parametric amplifier can be integrated monolithically. Higher-order frequency mixing. The above holds for processes. It can be extended for processes where is non-zero, something that is generally true in any medium without any symmetry restrictions. Third harmonic generation is a process, although in laser applications, it is usually implemented as a two-stage process. First, the fundamental laser frequency is doubled, and then the doubled and the fundamental frequencies are added in a sum-frequency process. The Kerr effect can be described as well. At high intensities, the Taylor series, which led the domination of the lower orders, does not converge anymore, and instead a time-based model is used. When a noble gas atom is hit by an intense laser pulse, which is an electric field strength comparable to the Coulomb field of the atom, the outermost electron may be ionized from the atom. Once freed, the electron can be accelerated by the electric field of the light, first moving away from the ion, then back toward it as the field changes direction. The electron may then recombine with the ion, releasing its energy in the form of a photon. The light is emitted at every peak of the laser light field, which is intense enough, producing a series of attosecond light flashes. The photon energies generated by this process can extend past the 800th harmonic order up to a few keV. This is called high-order harmonic generation. The laser must be linearly polarized, so that the electron returns to the vicinity of the parent ion. High-order harmonic generation has been observed in noble gas jets, cells, and gas-filled capillary waveguides. Example uses of nonlinear optics: frequency doubling. One of the most commonly used frequency mixing processes is frequency doubling or second harmonic generation. With this technique, the 1064 nanometer output from ND, YAG lasers or the 800 nanometer output from T, sapphire lasers can be converted to visible light, with wavelengths of 532 nm or 400 nm, respectively. Practically, frequency doubling is carried out by placing a nonlinear medium in a laser beam. While there are many types of nonlinear media, the most common media are crystals. Commonly used crystals are BBO, KDP, KTP, and lithium niobate. These crystals have the necessary properties of being strongly birefringent, having a specific crystal symmetry and of course being transparent for both the impinging laser light and the frequency doubled wavelength, and have high damage thresholds which make them resistant against the high-intensity laser light. However, organic polymeric materials are set to take over from crystals as they are cheaper to make, have lower drive voltages and superior performance. Optical phase conjugation. It is possible, using nonlinear optical processes, to exactly reverse the propagation direction and phase variation of a beam of light. The reversed beam is called a conjugate beam, and thus the technique is known as optical phase conjugation. One can interpret this nonlinear optical interaction as being analogous to a real-time holographic process. In this case, the interacting beams simultaneously interact in a nonlinear optical material to form a dynamic hologram, or real-time diffraction pattern, in the material. The third incident beam diffracts off this dynamic hologram, and, in the process, reads out the phase conjugate wave. In effect, all three incident beams interact simultaneously to form several real-time holograms, resulting in a set of diffracted output waves that phase up as the time-reversed beam. In the language of nonlinear optics, the interacting beams result in a nonlinear polarization within the material, which coherently radiates to form the phase conjugate wave. The most common way of producing optical phase conjugation is to use a four-wave mixing technique, though it is also possible to use processes such as stimulated Brillouin scattering. A device producing the phase conjugation effect is known as a phase conjugate mirror. For the four-wave mixing technique, we can describe four beams with electric fields, where EJ are the electric field amplitudes. I1 and I2 are known as the two pump waves, with I3 being the signal wave, and I4 being the generated conjugate wave. If the pump waves and the signal wave are superimposed in a medium with a non-zero I3, this produces a nonlinear polarization field, resulting in generation of waves with frequencies given by I perm L equals a plus or minus I perm L1, a plus or minus I perm L2, a plus or minus I perm L3, in addition to third harmonic generation waves with I perm L equals 3 I perm L1, 3 I perm L2, 3 I perm L3. As above, the phase matching condition determines which of these waves is the dominant. By choosing conditions such that I perm L equals I perm L1 plus I perm L2, I perm L3 and K equals K1 plus K2, K3, this gives a polarization field. This is the generating field for the phase conjugate beam, I4. Its direction is given by K4 equals K1 plus K2, K3, and so if the two pump beams are counterpropagating, then the conjugate and signal beams propagate in opposite directions. This results in the retroflecting property of the effect. Further, it can be shown for a medium with refractive index N and a beam interaction length L, the electric field amplitude of the conjugate beam is approximated by, where c is the speed of light. If the pump beams E1 and E2 are plane waves, then, that is, the generated beam amplitude is the complex conjugate of the signal beam amplitude. Since the imaginary part of the amplitude contains the phase of the beam, this results in the reversal of phase property of the effect. Note that the constant of proportionality between the signal and conjugate beams can be greater than 1. This is effectively a mirror with a reflection coefficient greater than 100%, producing an amplified reflection. The power for this comes from the two pump beams, which are depleted by the process. The frequency of the conjugate wave can be different from that of the signal wave. If the pump waves are of frequency I perm L1 equals I perm L2 equals I perm L, and the signal wave higher in frequency such that I perm L3 equals I perm L plus I perm L, then the conjugate wave is of frequency I perm L4 equals I perm L I perm L. This is known as frequency flipping. Common SHG materials: 800 Nm lighter BBO, 806 Nm lighter lithium iodate, 860 Nm lighter potassium niobate, 980 Nm lighter KNBO3, 1064 Nm lighter monopotassium phosphate, lithium triborate and I2 barium borate. 1300 Nm lighter gallium selenide, 1319 Nm lighter KNBO3, BBO, KDP, potassium titanal phosphate, lithium niobate, LiO3, and ammonium dihydrogen phosphate, 1550 Nm lighter potassium titanyl phosphate, lithium niobate. See also, Bornenfeld action, filament propagation, category, nonlinear optical materials, parametric process, notes. References, Boyd, Robert. Nonlinear Optics. Academic Press. ISBN A978-0-12-369470-6. Shen, Yuen Ron. The Principles of Nonlinear Optics. Wiley Interscience. ISBN A978-0-471-43080-3. Agrawal, Govind. Nonlinear Fiber Optics. Academic Press. ISBN A978-0-12-369516-1. External links, Encyclopedia of Laser Physics and Technology, with content on nonlinear optics, by Rawan Kortediga Pashopa, an intuitive explanation of phase conjugation, ADVR, NLO frequency conversion in KTP waveguides, SNLO, nonlinear optics design software, topics on photophysics and nonlinear optics.